If you've been training medical image segmentation models, you've almost certainly hit the same invisible wall: voxel spacing inconsistency. We spend months tuning architectures, experimenting with transformers and Mamba blocks, and fine-tuning loss functions. But the moment you load a dataset, you're forced to resample those volumes to a uniform spacing. And what do we use? Linear interpolation. It's fast, it's standard, and it's fundamentally flawed. Today, we're breaking down a new framework called Consispace, which treats voxel spacing consistency not as a boring preprocessing step, but as a learnable, semantic-aware optimization problem that directly boosts downstream segmentation performance. Let's be clear about why this matters. Volumetric medical data is inherently anisotropic. The slice thickness in the axial direction is often 2 to 3 times larger than the in-plane resolution. When you downsample, you lose information. But upsampling, that's an ill-posed inverse problem. You're trying to reconstruct missing anatomical detail from limited observations. Linear interpolation just draws straight lines between voxels. In practice, this creates jagged, discontinuous anatomical boundaries along the axial direction and smears semantic consistency across class boundaries. It's like trying to reconstruct a smooth curve with a series of disconnected line segments. State-of-the-art frameworks like nnU-Net and Total Segmentator all standardize this step, but they do it with a blunt instrument. This paper introduces Consispace, a framework that couples image resampling directly with segmentation objectives. Instead of treating resampling as an isolated upstream task, Consispace integrates 2 powerful constraints into an implicit neural representation backbone. First, an ODE-based anatomical constraint to model continuous interslice dynamics. Second, a dense feature reweighting mechanism using a pretrained vision model to enforce intraslice semantic consistency. The result is a resampling pipeline that doesn't just guess missing pixels, it reconstructs anatomically and semantically coherent volumes at arbitrary scales. Let's get into the math, because this is where the real innovation lives. The authors treat the axial slice index as a pseudo-time variable. Instead of discrete voxel-wise interpolation, they model the 3D anatomy as a continuous latent field QT, evolving over time. The evolution is governed by an ordinary differential equation. The partial derivative of q with respect to time equals a velocity field v, qt. In practice, they discretize this using an Euler method, but here's the clever part. They enforce bidirectional ODE constraints. You have a top-down evolution and a bottom-up evolution, each initialized from the first and last slice latents respectively. These are averaged, and then warped by an instantaneous velocity field that captures the difference between adjacent slices. Now, how do they compute that velocity field? They use a reversed attention mechanism. Standard attention highlights similarity, but here, you actually want to highlight discrepancy. By computing the pairwise cosine similarity between the previous slice's latent and the current slice's key, they invert it with a simple 1-s operation. High dissimilarity gets high attention weight. This forces the model to focus on where the anatomy is actually changing, making the interpolated transition between slices physically plausible rather than mathematically lazy. But interslice smoothness isn't enough. You also need class-wise semantic consistency within each slice. Consispace tackles this by freezing a pretrained vision model, specifically DINOV3, and extracting dense feature maps for every 2D slice. For any target coordinate, they compute a semantic correlation map by measuring cosine similarity between that point's feature vector and all others in a local window. They take the top k most correlated neighbors and perform a weighted aggregation to refine the interpolated features. This means the resampling process is actively guided by high-level semantic priors. If a voxel is being interpolated near a blood vessel boundary, the feature reweighting pulls information from semantically consistent neighbors, preserving sharp, class-coherent edges that linear interpolation would inevitably blur. Both of these constraints are baked into an implicit neural network. The encoder maps raw slices to latents. The ODE interpolator generates continuous temporal representations. The semantic reweighting refines them, and the implicit decoder takes coordinates and these enriched features to output the resampled intensity values. They train this with a combination of MSE and SSIM reconstruction losses against high-resolution ground truth pairs. The beauty of the INR formulation is that it supports arbitrary scale resampling without retraining. You just query the network at different coordinate scales. So does it actually work? The experiments span 3 major datasets: Spider for lumbar spine, Top Cow for brain vasculature, and BRA-TS for brain tumors. They compare Consispace against linear, cubic, and several recent volumetric super-resolution methods like cycle-INR and DP-INR. Consispace consistently tops the charts on PSNR, SSIM, and perceptual metrics like LPIPS. But more importantly, when you feed Consispace resampled data into segmentation backbones like nnU-Net, Swin UNETR, and even foundation models like MedSam2, you see significant dice score improvements and substantial reductions in Hausdorff distance. On the Spider dataset alone, nnU-Net jumps from an 81.64 dice with original spacing to 90.56 with Consispace. That's not a marginal gain, that's a meaningful shift in how we handle preprocessing. They also ran thorough ablations. Removing the ODE constraints drops performance noticeably. Swapping to unidirectional ODE evolution hurts. Replacing the reversed attention with vanilla attention degrades reconstruction. And tuning the local window to 5 by 5 with a top K of 5 gives the best trade-off between contextual richness and computational overhead. Parameter count stays lean at around 2.93 million, and inference is competitive with other INR-based methods. What makes Consispace compelling isn't just the numbers. It's the fundamental rethinking of a step we've blindly accepted for years. Medical image resampling doesn't have to be a disconnected, heuristic preprocessing routine. By coupling continuous ODE-based anatomical modeling with dense semantic priors, you get a framework that respects the physical reality of volumetric data while actively optimizing for the downstream segmentation task. As medical AI moves toward foundation models and multi-center datasets with wildly heterogeneous acquisition protocols, methods like Consispace will become essential infrastructure. The code is already public, so if you're working with volumetric medical data, it's worth dropping into your preprocessing pipeline and seeing the difference firsthand. Thanks for watching, and I'll see you in the next one.